Hi again, this is John with InventorCAM Professor, and in this series of Getting Started videos, I want to talk to you about defining geometries in iMachining 2D. I'm going to quickly run through some general examples of geometry definitions using this simple part. I'll then show you the iMachining toolpath techniques that are used on each of the geometries. Now, one very important thing that you should keep in mind is that the geometry in iMachining is defined as a pocket that can be closed, open, or semi-open, meaning containing open edges. Of course, there can be many different configurations of pockets, containing internal chains that are treated as islands or used for safe tool entry. In any case, though, the geometry is defined in such a manner. Now, as I define the different types of geometries, you'll also notice that the chain selection order is pretty important, so just keep that in mind. So I'll start off with examples of closed pocket geometries, and then I'll get into the other two types. As you can see, I have my example InventorCAM part loaded and ready to go. The CAM part and iMachining data are defined, and I've even defined the tool I'll be using for this CAM project. I'll start off with the simple closed pocket in the back left corner. And then I'll just work my way down the line from left to right. I'll go to the InventorCAM Manager, where I can right-click Operations, Add Milling Operation, and select 2D iMachining to add my first iMachining operation. The first and most important thing I have to do, which is pretty fitting for this series of videos, is define the machining geometry. So to do that, I'll simply click the New button on the Geometry page. Now for all the upcoming geometry definitions, I'll have to perform some chain picking. You'll see that there are several methods to do this. Now because these are 2D geometries, you'll notice that I will always be using the option of Auto Constant Z. After picking my initial contours, this option will quickly and easily close each chain by automatically selecting all connecting entities on the same Z level. For this first example, the geometry is defined as a simple closed pocket. In the graphics window, I'll pick on the lower contour of the pocket, select Auto Constant Z to close the chain, and then click Yes to accept the chain selection. Finally, I'll click Finish to confirm the geometry definition. Next, I'll define the tool by switching to the tool page and then clicking the Select button. When the part tool table appears, I'll choose the already created 8mm end mill from the list and then click Select. The last thing I need to do is define the milling levels. So I'll move down to the Levels page, where I'll click the Upper Level button first. Then in the Graphics window, I'll pick on the top face of the stock model. This is the Z level where the machining will start. Clicking OK will confirm the selection. I'll click the Pocket Depth button next to define the machining depth. I'll pick on the bottom edge of the closed pocket, and then I'll click OK to confirm the selection. Now, those are the only definitions I need to make. The iMachining technology does the rest. As you watch more of the Getting Started videos, you'll see in more detail how things are being done. Let's just focus on the geometry definitions for now. With that said, I'll name the operation Closed Pocket. I want to keep things organized and later provide you with the completed CAM part so that you can take a look at what I'm doing here firsthand. When I click Save and Calculate, this iMachining operation is added to the CAM tree and the toolpath is calculated. I'll then click the Simulate button to open up the Simulation Control Panel. When I click Play, we'll see that iMachining uses the helical data from the operation to enter the closed pocket, followed by a morphing spiral to the outer walls. When the wireframe toolpath comes to an end, I can exit the Simulation Control Panel. Now I can define the next iMachining operation. Since all the examples in this series of videos will use the same tool and have the same exact depths, I'll make it easy for myself by clicking the Save and Copy button. This will automatically create and open a new iMachining operation. All the definitions from the previous operation will be copied over. The only thing different I have to do is define the new machining geometry. I'll be doing this for all the examples moving forward. I'll click the New button to start the geometry definition. I'll pan over to the next pocket. Now for this operation, the geometry is defined as a closed pocket with island. In this case, I have to define two chains. The first chain to select is the pocket contour. And the second chain to select is the island contour. Finally, I'll click Finish to confirm the geometry definition. I'll name this iMachining operation Closed Pocket Island. And then I'll click Save and Calculate to add it to the CAM tree and calculate the toolpath. Then I'll click Simulate to start the simulation. After I click Play, you'll see the tool perform a helical entry. A moat, which is a unique feature of iMachining, then separates the island from the remaining material so that a morphing spiral can then be formed. So there you have it. I'll exit the simulation control panel and then click Save and Copy to start a new operation with the same settings. I'll click the New button to define the machining geometry. First, let me just move over to the next pocket. Now for this operation, the geometry is defined as a closed pocket with multiple islands. Now, there are only two islands in this example, but an unlimited number of islands can be defined. So just keep that in mind. So here I have three chains that I need to define. The first chain to select is again the pocket contour. And the next two chains to select are the island contours. These can be picked in any order. And finally, I'll click Finish to confirm the geometry definition. I'll name this operation Closed Pocket Islands. I'll click Save and Calculate. And then I'll click Simulate to start the simulation. When I click Play this time, the tool enters the pocket in the same way as before. Now we can see that each island is separated when encountered and a final morphing spiral is formed. Now I'll exit the simulation control panel and then click Save and Copy to start another operation with the same settings. I'll click the New button to start the geometry definition, and I'll move over to the next example. Now for this operation, the geometry is defined as a closed pocket with entry geometry. Keep in mind that any shape can be used as entry geometry given that it is located inside a closed pocket. Again, the first chain I have to select is the pocket contour. The second chain for me to select is that of the entry geometry. However, now I have to right-click Chain 2 in the chain list of the Geometry Edit dialog box and choose Mark Chain as Open. And that's it. The chain turns green in color, and now iMachining is informed that the geometry can be used for entry and that it's not an island. So I'll click Finish to confirm the geometry definition. I'll name this iMachining operation Closed Pocket Entry. I'll click Save and Calculate, and then I'll click Simulate to open up the simulation control panel. Now when I click Play, the tool is shown feeding down into the open area, and from there a morphing spiral is formed to the outer walls of the pocket. And of course, now I'll exit the simulation control panel, and then I'll click Save and Copy to start another operation with the same settings. When the copied operation opens, I'll click the New button on the geometry page to define the new machining geometry. I first have to pan over to the next example. For this operation, the geometry is defined as a closed pocket with entry hole. This shows how to define an entry hole that was previously drilled. The geometry for this example is defined exactly as before. The first chain I have to select is again the pocket contour. The second chain to select is the entry hole. Since it's already closed, I don't have to use the option of Auto Constant Z. I can just click Yes to accept the chain selection. Again, I'll right-click Chain 2 in the chain list and simply choose Mark Chain as Open. Now I can confirm the geometry definition by clicking Finish. I'll name this iMachining operation Closed Pocket Entry Hole. I'll again click Save and Calculate, and then I'll click Simulate to open up the simulation control panel. When I click play, the tool is shown feeding down into the hole, and just as before, a morphing spiral is formed to the outer walls of the pocket. Now I want to mention something very important. If the pocket has a flat bottom, then the hole should have a flat bottom also, since the tool will feed down to the bottom of the hole. In such instances, a profile operation can be used to remove the drill point from the bottom of the hole prior to using iMachining. And now I want to exit the simulation control panel and then create a copy of the current operation with the Save and Copy button. After the copied operation automatically opens, I'll click the New button to start the geometry definition. Of course, first I have to move over to the next example. Now for this operation, the geometry is defined as a closed pocket with island and entry hole. Nothing too tricky here. I'll start off by selecting the first chain, which is again the pocket contour. Then I have to select the following two chains: the chain on island contour and the entry hole chain. And again, the order of these two internal chains doesn't make a difference. In the chain list, I'll right-click the entry hole chain, chain 3 in this case, and choose Mark Chain as Open. I'll click Finish to confirm the geometry definition. I want to name this iMachining operation Closed Pocket Island Entry Hole. Then I'll click Save and Calculate, followed by clicking Simulate to open up the simulation control panel. Clicking Play shows the tool first feeding down into the hole, then separating the island from the remaining material, and then finally forming a morphing spiral to the outer walls of the pocket. Moving on to the last closed pocket example, I'll first exit the simulation control panel and then make a copy of the current operation by using the Save and Copy button. After the copied operation opens, I'll click the New button to start the geometry definition. I'll now pan over, and for this operation, the geometry is defined as a closed pocket with multiple islands and an entry hole. I'll start off by selecting the first chain, which is again the pocket contour. Then I'll select the chains on island contours, followed by the entry hole chain. And again, in the chain list, I'll right-click the entry hole chain, chain 4 in this case, and choose Mark Chain as Open. I'll click Finish to confirm the geometry definition. This iMachining operation I'll name Closed Pocket Islands Entry Hole. I'll then click Save and Calculate, followed by clicking Simulate to open up the simulation control panel. When I click Play, the tool feeds down into the hole just as it did previously. This time both islands are separated, and then a final morphing spiral is formed to the outer walls of the pocket. Well, that just about does it for the closed pocket geometry examples. Of course, these examples are fairly basic, but hopefully they give you good insight to how closed pocket geometries are defined in iMachining and some of the techniques that are used when cutting those geometries. So check out the next part, where I'll show you how a few different types of open pocket geometries are defined in iMachining.